Alright, hello everybody. So this is our second chapter. It is matter and energy. This first lecture that I'm going to give to you is all about what matter is and some definitions about it. We're going to also talk about different types of matter, elements, compounds, mixtures, how they can be divided up into different phases, and also how to separate mixtures. So that's pretty much as far as we're going to get for this first video. So the first thing that you really need to understand, what is matter? And so the textbook definition, when I think about what matter is, I think about it having two main qualities. One is that it has mass, and the other is that it has a volume, or it takes up space. So it's anything that has mass and takes up space. If it, follows these two properties, then it will be considered to be matter. Now, matter can be subdivided into categories, and the main category is either you're a substance or you're not a substance. Now, if you're a substance, you're considered one of two things. A substance can either be a compound or it can be an element. And we're going to define these in the table below. But something important about both of these is that they are considered to be homogeneous. So what does it mean to be homogeneous? Well, for us, and you may have a definition and you may have heard the term, Homo sapien, in biology, you've heard hetero and homozygote. And so for us, homogeneous means that, or homogeneous means that you are uniform. You have a uniform composition. So when I look at a substance, when I look at, like an element or a compound, it should look the same throughout the entire sample. There shouldn't be differences. There shouldn't be certain areas of it that have a certain texture or a certain look to it and other areas that you're not. Now, the main law for matter that we will always follow is the law of conservation of matter. And what this means is that, when you have a normal chemical reaction or a physical reaction, and I'm going to use the word change for now, the amount, so the total amounts of all the atoms does not change. So for example, if I were to take some hydrogen and I were to react it with some oxygen and I were to make water, I would need to balance this equation so that I would have the same amount of oxygens and the same amount of hydrogens. Now, you don't have to know how to balance equations just yet. We haven't gotten there. We'll do that in probably in another month or two. But for now, looking at this, if I were to say, well, how many hydrogen atoms do you have on the left? If you multiply the large 2 by the small 2, you will get 4 hydrogen atoms. And if you do that on the right, you multiply the large 2 by the small 2, you will also get 4 hydrogen atoms. When we look at the oxygens, if you multiply the 1 that is invisible but is known to be in front of the oxygen, you will have 1 times 2, you'll have 2 oxygens. And on the other side, you'll have 2 times 1, you'll have 2 oxygens. So the amount of atoms are the same on each side, and that is how we see the law of conservation of matter in chemical and in physical changes. Now, if you're wondering what a chemical and physical change is, we're going to do that in the next video. So this slide is probably the most important slide of this particular lecture. When I look at this, I have my element, my compound, my mixture. You really need to have details about each one. So for an element, important is that, first of all, you can find these on the periodic table. Hopefully you've been doing your memorization of these elements, but you find them on the periodic table. They are made up of identical atoms. So all the atoms in an element are the same. If I have sodium, well then all of the atoms in that sample of sodium are going to be the same exact atoms. Another important thing about an element is that it cannot be broken down chemically. So I cannot make it anything smaller chemically, otherwise it loses its identity of that being that element. And so for sodium, for example, if I were to draw a picture of it, because it's important that you know how to do particle diagrams, so if I were to have a box and put some sodium in there, since sodium is a solid, all of the atoms would be grouped together like this, and they would all be identical. There are other elements that I can put in, like for example, if I were to have, some xenon and put it in a box of a similar size, all of those would be floating around. Xenon's a gas. Now, how do I know xenon's a gas versus sodium being a solid? Well, we're not there yet. But, in a few weeks, when we talk about periodic table, another month or so, we'll talk about, well, which elements are solid, which elements are not solid, which elements are gases and liquids. So, if I were to go to a compound, with a compound I have two or more different elements. Chemically combined. And the different is really key, because there are certain elements that actually can exist where there's two or more of the same element chemically combined. And if I take a second here to show you some of them, there's actually 7 of them that exist as something called diatomics. And they include bromine, with 2 bromine atoms attached, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. I call it the Brinkelhoffs. You can ask Jared Akunowicz about that. And so when I look at this, if I were a nitrogen, molecule, because I'm 2 atoms, I would have my 2 nitrogens and they would be attached to each other, but they would be identical. You're going to see when we do particle diagrams of a compound that those actually are 2 different atoms, so we're going to draw the circles different. So these are 2 or more different elements that are chemically combined in a compound. And something really important about it is that they're in a fixed ratio. So what does this mean? Like, for example, if I have water, H2O, that's 2 H's and 1 O. But if I have another compound that has hydrogen and oxygen, H2O2, it's a completely different compound. This is water, H2O. Hopefully you know what H2O2 is. If you don't, I'll tell you it's hydrogen peroxide. Actually, I guess you wouldn't know what that is just yet, but you probably have heard of hydrogen peroxide. Maybe you don't know the formula. So just imagine that I change one of those oxygens, or I add another oxygen on. I go from having 1 oxygen to 2 oxygens. And magically I become a different compound. And they're hugely different. Water, I need it. I need it to live. In fact, I'm going to take a drink right now. Hydrogen peroxide, it's toxic. I can't drink hydrogen peroxide. It's an antiseptic. I actually put it on cuts and scrapes. It bubbles. It's in very small amounts in mouthwashes. It's in pretty strong amounts in things like pool shock. But water is necessary for life. And it's that 1 oxygen difference that separates these compounds. They have a fixed ratio. You change that ratio, you change what the compound is. So now, if I were to draw a particle diagram, so if I were to draw water's particle diagram, I draw a box. And if I wanted to draw the molecule, I would have 1 circle that would represent oxygen, and another circle, or 2 circles, that would represent the hydrogens. They have to be different shapes, or different colors. So I could do something